So yeah, hi guys, I hope you had a great day. Today we're just going to look at an application of using our integrals. Now, I want you to think about this as being really the same as what we did with our differentiation. Considering, we do exactly the same thing, so the second derivative means the same thing as what it did before, and the first derivative means the same thing. The only difference with these questions is we're starting with maybe the first derivative or the second derivative, and we've got to integrate to work our way back to the function. Alright, so that's how these sort of things work. Now, looking at this question here, pretty classic sort of question. We've got a water pipe, we've got water going through where I'm actually showing you there. The thickness of this particular pipe is in fact 3 centimetres, so when we're looking at that, so this point here is the 3 centimetre mark, and then that's the 6 centimetre mark. Now, the question's about finding what the temperature of the pipe is on the outside. And that would be useful, obviously, if you want to look at how hot that pipe gets and how you might need to insulate it. So let's start by having it go like that. So here's my function there, what I've got. I'm going to need to, for this function, I'm going to need to integrate that to try and get my equation. So now I'm going to write this slightly different. So if we want to work out what dt is, that's going to be the integral of minus 20. I'm going to bring this up as a power and make it negative 0.63, and then we're differentiating it with respect to x. Alright, so if I do my integration, then what I need to do is obviously add 1 to that, so that will become negative 20 x to the 0.37, and that's all then going to be over 0.37 plus our c value. Alright, so that is pretty well what t of x is actually equal to. Now, one thing that we do know is that when x is equal to 3, we know that t is equal to 100, don't we? Alright, so we can put that into the equation. So 100 is equal to minus 20 on 0.37. Now, x is going to be 3 to the power of 0.37 plus our c value. Alright, so if I do that calculation, bring it across, that will tell me what my c value is. So let's do that. So 20 divided that by 0.37. I'm going to times that by 3 to the power of 0.37. Enter. So when we add 100 to that, we know that our value of c is equal to 181.16. Alright, so going back to our thing, so therefore c is equal to 181.16. So I can rewrite my equation t of x is equal to minus 20 all over 0.37 x to the 0.37 plus 181.16. Now, I think that works out to be roughly about 54 if you want to write that. So it might be a better way of writing that as minus 54. Okay. Next bit, what we want to do is we're interested in finding what the temperature is at the 6 mark. So that we need to then use our equation to work that out. So put that into there. 6 to the power of 0.37 plus 181.16. So we've already got that on our calculator. So if I have 54, it's actually minus 54, isn't it? Times by 6 to the power of 0.37, and then we have to add on our answer, which we just had before, so plus our answer on. That will give me 76.37. Alright, so that's equal to 76.37, and degrees C is my answer there. Alright, so that question really asks you to get back to your original function based on the fact that you were given your first derivative. Alright, so good example, not that hard. It also relates to, and you could also ask things like the rate of change and all that sort of stuff from your equation there. Second equation, where we've got here, second question, we've got a plank which is 4 meters long, and it's fixed at point 0 and P, and we know those coordinates. So if we know 0 is going to be 0, 0. We know that P is going to be 4, 0. We need to use those later on in the question. The sag of the beam there is given by this equation here. Now that's obviously the second derivative, so what we'd be looking to get is an equation with y is equal to the value of x. Alright, so that's what we need to do. Now keep in mind, in the building industry, if you're building a house and you need to put a big beam across, then they have specifications to look at the thickness of the beam and how it's orientated, so you can actually minimise, or not minimise, but eliminate the sag. Alright, so obviously this would be for a beam that's not necessarily that thick. So first thing I need to do is I need to get an equation that measures the sag. Because it's a second derivative, I'm going to have to integrate this twice. Okay, so I can say that my dy dx is equal to the integral of, now I'm going to put the point 1 through, so I'm going to say it's equal to 0.02x take 0.01x squared on 2. Okay, and now I have to integrate that with respect to x. So when I do that, I'm going to get something like this: 0.02x squared on 2 take 0.01x cubed on, that's going to be 3, so it's going to become 6 plus c. Okay, so that's my first derivative. Now I don't know what c is. Now to work out what my y value is, my y value is going to be the integral of that. Alright, and I'm going to now do that with respect to, I'm just saving time, you wouldn't write it like this, but just to save some time. I'm now going to do the same thing. I could cancel that out there and make that a 1, I suppose. So when we integrate that, it's going to be 0.01 x to the 3 on 3. Then I'm going to do the same thing over here. It's going to be 0.01 x to the 4 on, what's that? x4 on 24. And then that's going to be cx plus d. Alright, so we don't necessarily know what that is, but we have to find, obviously using some information, our c and our d values. Alright, so this is the equation of y that relates our thing over here to the sag. So the first point that we do know is 0, 0. So if we put y equals in there, all of these values with an x are going to go out, and that's going to say d is equal to 0, which is really nice, so that means that goes out. The next equation I'm going to use is 4, 0. So therefore y is equal to 0.01 4 cubed all over 3, take 0.01 4 to the power of 4 over 24 plus 4 times by c. Alright, and we actually know that's equal to 0, don't we? Alright, so it's a matter of then going to my calculator and doing that. So it's 0.01 times by 4 to the power of 3, so it's 4 cubed, times by 4 to the power of 3, and then I have to divide that by 3. Now the next term I have to take away, so it's going to be take 0.01 times by 4 to the power of 4, and then I have to divide that by 24, not times, divide, and then I need to work that out, so that will give me that value there. Now if I actually put that into a fraction, that one might be a bit easier. Okay, that gives me 8 on 75. Okay, so if I go back to this thing over here, alright, so this all here now becomes 0 is equal to 8 on 75 plus 4c. So therefore, we know that 4c is equal to minus 8 on 75. And so therefore, cancel the 4's out, therefore c is equal to minus 2 on 75. Alright, so in terms of our equation, I think that certainly makes sense with what we're doing, alright, with what we've got there. Now, so I can rewrite that equation. We can say that y is equal to 0.01 x cubed on 3, take 0.01 x to the power of 4 on 24, and then we've got to take 2 on 75 x. Alright, so that's the equation I need to use when I'm doing the rest of these questions. Keeping in mind that's relating the y value, which is a representation of the sag, for the x value that I've got. Now, the second part of this question is to look at the sag, the maximum sag. So the maximum sag that we're going to get is in the middle, and that's going to be when x is equal to 0. Not 0, when x is equal to 2. Alright, so maximum sag when x equals 2. So y is equal to 0.01, and that's going to be 2 cubed on 3, 0.01, 2 to the power of 4 on 24, take 2 on 75, 2. Alright, so if you go put that into your calculator, it's not a hard calculation to do, and I know you can do it. You're going to get an answer of 0.0333. Alright, so that will give you an answer of 3.33 centimetres. Okay, so that's the maximum sag for my beam coming down. The next part says we want to work out the sag when it is at a distance of 1 metre from P. Now, if you go back to your diagram, you know P is at the 4 metre mark. So therefore, we're looking at the 3 metre mark. So we're saying x is equal to 3 metres. Alright, so if we go and do that again, we'd have to say x is equal to 3. So y is equal to 0.01, 3 cubed on 3. Take 0.01, 3 to the power of 4 on 24. Take 2 on 75 times by 3. So again, if you put that into your calculator, you do all the work, you're going to get something like 0.02375, which is equal to 2.375 centimetres. Alright, so that's fairly easy calculation to do. One other way of doing that would be putting that model into your calculator, and then you can just use your x value, and that will tell you what your values are. So that may be a quicker way of doing it than doing all the algebra. Keeping in mind, all we're really interested in is the answer. Okay, so you get really only 1 mark for doing that, and you only get a mark for doing the answer. So you want to do that as quick as possible. The last question is part D. We have to work out what the angle of the plank makes with the horizontal at the 1 metre mark. Okay, so we would need to work that out. If we do a little bit of a diagram, might help us here. All right, so obviously we've got our plank. Our plank is bowing a little bit like this, so I overemphasize it. We know at this point here that there is in fact got a distance of 2.375 centimetres. Okay, we know this distance here is 100 centimetres, isn't it? Right, so if we've got that diagram, what are we interested in? We're interested probably in this angle here. So obviously you're going to use tan, so tan of theta is equal to opposite, so that's 2.375 all over 100. So theta would be equal to inverse tan of 2.375 all over 100. So go to your calculator and do that. Yeah, it's in degrees. So inverse tan of 2.375. Divide that by 100. Not 1,000. and that gives me an angle of 1.36. Okay, so that's what I'm looking at in terms of my angle, 1.36 degrees. Okay, so that's the angle it makes with the horizontal if I had a line there going there. I hope this helps you. Essentially, you're not really doing anything new. All you're still working with is the functions. The key to these questions is that you've been given the derivative or the second derivative, and you need to get back to the original equation to solve it. So good luck with those questions. They are worthwhile having a go at a whole range of those, and make sure you either use the revision guide or come and see me if you need some help with those. So I'll talk to you later. Good luck with those.